go to 15. So we're at the almost at the end of the book. Today we're gonna discuss about chapter 8, which is dataset engineering, and next week about inference optimization. So that's the agenda for today. So dataset engineering. Speaker. You see a screen, right? Should be full size now. Yep. So dataset engineering, as I said in the Discord message, very relevant chapter, and also relevant not only in AI but also traditional ML benefits a lot from what is said in this chapter. But yeah, most of it applies even about data analysis and stuff. So we'll talk about the basics, data curation, data augmentation and synthesis, and data processing. Maybe the most AI-related part is this part. And the rest, I would say, applies for almost everything in data, or anything, any job that has to deal with rows and columns, or images or text. So the goal of data engineering is to create a data set that allows you to train the best model possible. So you have a set of data. What are these steps that you need to do in order to create a good model? As you might know, the quality of the model depends on the quality of its training data. So the job of the model is to try to replicate, to find a function that goes from input to output in the training data. So if the input and output of the training data are bad, then that relationship that the model is going to learn is going to be bad, right? There are some dedicated roles that came out with all of these advances that are related to data specifically. Those are data labelers, data set creators, and data quality engineers. In small companies, most of these tasks are done by the same person. Bigger companies, they can even like outsource some of this. Like for example, data labelers. There's this very popular company, very big, called Scale AI, which is a company that very big companies use to label their data. So they can have a bunch of prompts that they gather from data in order to take a bunch of instructions, and they have people labeling it. One of the most popular services for training like OpenAI models, Cohere, Anthropic, everything basically. So yeah. In the chapter, we will focus on post-training data, meaning data that is used for fine-tuning purposes. It doesn't discuss much the pre-training data because we already kind of discussed that a little bit, but that's assumed that you will basically gather large corpus of data. So data basically from the whole internet, Wikipedia, etc., forums. So that's the data that you use like long sequences, mainly to train your model in a self-supervised fashion. And the data that we'll discuss here is the one that you have supervised learning, right? You have examples and outputs, inputs and outputs. So yeah, usually training data is measuring number of tokens, and usually fine-tuning data is measured in number of examples. The chapter discussed a little bit about model-centric and data-centric AI, where model-centric is, as the title says, it focuses on the model. So it says, okay, enhancing the model, improving the architecture, increasing the size, or developing new techniques is something that improves the model. So there are labs that focuses on that. And there are others that focuses, okay, we have this architecture and let's try to enhance our data so we can squeeze or take out as much as we can from this architecture by having the best data set or a high quality data set. Both of these ways of doing things improves at the end the model. Of course, in an ideal world, you do both, right? You create the best architecture possible, split of the edge, like the state of the art architecture, and you have a high quality data set. But yeah, you always kind of lean towards one or the other. Sometimes what's commonly happens is that a lab finds a very nice, like a state-of-the-art architecture that performs really well, and then other labs start uh, creating high-quality data sets and even like having better results than the original lab, the original architecture model that the original lab created. Of course, during the chapter, but it's focused on a data-centric fashion way. So, as I said, we'll discuss about data set creation, data augmentation, and data processing. So let's start with data creation. So creation is a science that requires understanding how the model learns and what resources are available to help it learn. So in simpler words, it means that the right data can make the model more capable, safer, and able to handle longer contexts. So poor data, as we know, can cause model to increase biases and hallucinations. And so data creation is the art, the science, kind of like designing those, gathering the best examples that for your model. Just a second. Oops. Okay. So what data you need, it's gonna depend totally on your use case, on your task. So if you just want to do self-supervised fine tuning, you'll probably be okay with just sequences of text. If you want to do instruction fine tuning, or like for training a question and answer model, you will need pairs of instructions and responses. If you want to do preference fine tuning, you will need instruction, the winning response, and the losing response. If you want to train a reward model, you will need the instruction, the response, and also the scores. So yeah, data creation is all about this, matching your data to whatever task you want to do. So for example, your data should exhibit the behaviors that you want your model to learn. So let's say you want a question answering model where you send a question and the model just responds with a specific response, a short response. So you want a model to just give you short responses, your training data should have short responses, right? If you want a model to be trained in a chain of thought fashion, you need instructions that say so, like, okay, reason and do a step-by-step analysis. And your response in the training data should also look like your desired output, right? So the model in the response, that the data set should have examples that say, hey, so yeah, you have 23 minus 20 is equal to 10 to 3. So they do like the whole analysis in the in the response. So if your data should look like the behavior that you want your model to have. Also, if you want, so for example, if you want an application, a conversation interface like ChatGPT, and you want your model to handle single turn versus multi-turn uh, responses or interactions, your data should also have, right? Single turn means that you just ask a question to the model, and the model responds. Multi-turn behavior means that you send a question to the model, and maybe your question wasn't that clear, and your model responds like, "Hey, do you mean X, Y, or C?" And the user responds, "Ah, no, I mean Y," and the model says, "Ah, okay. So given that you mean Y, then the outcome is this." So that's a multi-turn data. So if you want your model to handle those kind of behaviors, your data should support, should have coverage, which is something that we'll discuss later in the chapter, should have coverage for those examples as well. So more about data curation, there are some criteria. So first, data curation is not just about creating new data. It also means removing existing data that doesn't help your model. So you can help it unlearn bad behaviors. For example, if you only want the chain of thought instruction and you have data that looks like this, then you need to remove it, right? Because it doesn't support the behavior that you want for your model. That's a criteria. But basically we can split everything into three criteria, which are data quality, data coverage, and data quantity. In the chapter, Chip makes an analogy, a cooking analogy, for these three criteria, and she says data quality is like having quality ingredients to cook a meal. Very easy to understand. Data coverage is having the right mix of ingredients. So you don't just need high quality ingredients. So if you want to prepare, I don't know, what's something that we can cook. If you want to prepare a pizza, uh, you don't need. I mean, you can add a lot of things to a pizza, but if you don't have yeast, then you won't have a good pizza probably. If you don't have water, also, no, you could have like caviar and a lot of other high quality ingredients, but at the end, if you don't have the right coverage of the ingredients that you need to make this specific pizza, your model is not going to be good, meaning your meal is not going to be good. So you need high quality ingredients, the right mix of ingredients, and then the right quantity, right? Uh, you cannot make if you are just making one pizza, maybe yeah, you can have a low quantity of each of the ingredients, but if you want to make 100 pizzas, you will need probably lots of water, lots of tomato sauce, lots of cheese, etc. Right, and lots of each of those things. So those three things are also important when creating a model. Okay, so let's break down each of these. Let's start by data quality. Um, Something that is good and bad is that a small amount of high quality cannot perform a large amount of noisy data. So there was this paper of John and company where they crafted 10,000 instructions, very nice ones, and found that it gave superior results than just having hundreds of thousands of noisy instructions. So that's something good in the sense that, okay, yeah, to get good results, you don't need like lots of data. The sad part is that having 10K carefully crafted instructions is often quite expensive, right? You need often humans to just go and write those instructions or review those instructions, and that always takes time, and that translates to money. So almost everybody understands what data quality means, but what exactly does what exactly is means that the data is high quality. The short and complex answer is the data is considered high quality if it helps you to do your job efficiently and reliable. The long answer is that high quality data needs to have all of these things. Needs to be relevant for the task that you're doing, needs to be aligned with the task, needs to be consistent, needs to be correctly formatted, unique, and compliant. Let's check each of these. By the way, if you have any questions, just unmute yourself and let me know. I see a question in the chat. That's also true what Michael said, that there are like new techniques that you can get very good results with few examples. That's something that is seen with PET methods, parameter efficient fine tuning, right? Yeah, parameter efficient fine tuning. Often we need less examples than with like the traditional methods. So let's check each of these criteria for data quality to be met. So the relevant means that training examples should be relevant to the task that you're training. Very relatively easy to understand, aligned with the task requirements. So for example, if your task requires creativity, the annotations should be creative as well. If the task demands not just a score, but also a justification of that score, data annotation should have the score and the justifications as well. Consistent. If you have two annotators working on the same example, then their annotation should ideally not be too different. Correctly formatted, all examples should follow the format expected by the model. So this can mean, for example, like if your model only accepts a specific tokenizer, so during the pre-processing, you should tokenize your model in that, your data in that way. Or it also can mean like if you expect your model to output JSONs, like this is a model that you use for, I don't know, for coding and stuff like that, and you want your output to be a JSON file, then your training data, the outputs of training data should also be formatted in JSON, right? And have the correct syntax. Sufficient unique, it means that like in model training, duplications can often introduce biases and cause data contamination. Data contamination in the sense that let's say you have 100 examples and only 50 are unique. So let's say each example you have a duplicate, right? And you do a train test split of your data, and 50 goes to training, 50 goes to test, and the same examples are in both in training and in test. So then you will get a like perfect score between test and training and test. So your data, your performances will be exactly the same, and you're gonna say, I'm not overfitting because train and test is the same. So everything looks great. But actually what happened is that there was some data contamination due to duplicate records, right? Because you are just fooling yourself because basically your training data is the same as your test data. So with more duplicate records, that increases the chances of that kind of contamination. Uh, Compliant, then high quality data needs to comply with basically laws. Uh, this means that your data should be compliant with all relevant internal or external policies, like regulations and laws. So that's high quality data. Any questions? Nope. Then continuing with data coverage. Um, Remember, data coverage in the cooking example is having the right mix of ingredients, right? So in terms of data, a model's training data should cover the range of problems that you expect it to solve. Here are some examples. So for example, if a user typically have typos when they write the prompt, so your example should also have typos. So it understands what the user is asking. If your application works with multiple programming languages, then your training data should include the programming languages that you expect users to use, right? That means having coverage for those programming languages. If you have a French to English tool, then uh, you don't need you don't need to have coverage for other languages. You don't need Spanish or German because users will know that this specific tool is just for French to English. But you will probably benefit from having diversity in topics, length, speaking styles, right? So, but everything in the context of French to English. Let's say what Michael says. Michael said, in my experience, data coverage isn't usually something you solve once. It is usually an incremental cycle of discovering weaknesses in your model, identifying how you can improve your coverage, retraining, and repeat. Yep, that's nice. Thanks, Michael. That's a nice comment. Yeah, it's not. Yeah, also with data, if you want to always continue like improving your model, you have an initial data set, right? You try to have high quality, high coverage on the topics that you think users will care about. Then you put your model into production and you start finding like some holes on your model. And maybe there's not enough coverage of things that you didn't expect your users to do, but they end up being like beneficial. So you want to increase coverage in those topics. So yeah, good comment. But yeah, that's coverage. Basically having the right mix of ingredients that you expect users to care about. Then data quantity, also relatively easy to understand from the name. Usually we know that, okay, the more the better. Chip adds this nice sentence where she says that asking how much data you need is like asking how much money you need. Basically, you can just go plus infinity. Um, but it also depends on what do you want to do. It Depending on what you want to do, you might not need that much data. You might have a good results with few examples. So, for example, if you want to do fine tuning and you want to do a full fine tuning of a big model, then probably yes, you need a lot of data, right? Because you're doing a full fine tuning. But if you are doing parameter efficient fine tuning techniques, then you can you can just use fewer examples than if you have to do a full fine tuning. It also is going to depend on the task complexity. So if you're doing a simple task like classifying whether a product is positive or negative, a product review is positive or negative, then you don't need that much data. Also, the examples are gonna be relatively easy to find and easy to label. But if you are training a model to answer questions about financial feelings, you will need probably more data because this task is more complex. If you're starting from a base model that is already good and you want to just make it a little bit better, you just with a few examples, few high quality examples, you can get it there, right? Because you are starting from a very good base. So data quantity also depends a lot on what you're actually doing. But yeah, some nice experiments with data quantity. Um, Here we have 5 models, uh, different sizes, different like more. This is more advanced, for example, than this model, and we see that with little data, yeah, the most advanced model, like advanced models are the better. But there's a point where you just continue adding lots and lots of data, and even the weaker model becomes very similar to the advanced model. So this explains how, yeah, there's like this balance between complex and advanced models and data. So if you have few examples, you can probably just uh, make it like you can probably have good results with advanced models and few examples. But if you have lots of examples, if you just use a simple model, then you will get almost the same performance as the advanced examples, and that's good because then it's the simple model is probably like cheaper to host, cheaper to run, faster, etc. There's also this nice experiment that you can do yourself when training a model and don't have enough data and you want to see if just investing more time in finding more data would give you like some performance gains. So, for example, if you have a data set of 100 examples or 1,000, I don't know, whatever number. Let's say you take 25, you train your model, you record the performance, and it's around you, 25 examples. Then you add 25 more. So you train your model with 50 examples, and you see a performance gain here. Then you train your model with 75 examples, and your performance still continue going up. This is telling you, okay, if I continue adding more examples, my performance is gonna improve. Then you add 100 examples, and it goes, there's a gain as well. Then you go and find 200 examples. You label more data, etc., and you see a performance gain. Then you say, okay, the trend is continuing. Then you go and add 100 more. You have 300 examples, and then your performance here. You add 100 more, then you have 400 examples, and your performance kind of plateau there. So you now see, okay, there's a plateau here. Probably if I go spend more money, more time in another 100 examples, my performance is just gonna be slightly better. It's the gain, the slope is not gonna be as big as it was in the beginning. So I'm happy with this. This is something that you can do with your own data sets. Just start. If you have like 10,000 examples, you can do it um, and see if there's any benefit from continue adding more data. Uh, the pattern is usually looks like this, and then you're just restricted by your model architecture, basically, or might be that by the data quality inside your data model. Um, okay, that's about the first section. That is, I know. Yeah, we haven't talk about data acquisition and annotation. That was it. then it's about augmentation synthesis. Correct. Okay. So data acquisition and annotation. Yeah, acquisition means you're just gathering data. You can do it by three different methods. Uh, just public data, internet data, uh, buying some data from different sources, uh, annotating data, synthesizing data, something that we'll discuss later on. Uh, if you create a way, if you can find a way to kind of create a data flywheel where every time your user interacts with the application, you store the data and then you can use it to continuously train your own model, then you are in the like sweet spot. You're in a very nice position because then that data is super relevant for your use case because it's actually like data from the interaction with the user. So you end up with data that is relevant and aligned with your task. So that's about data acquisition and annotation. Chip has a nice example of how this this process looks like. Of course, an ideal example and something that just linear in real world, like you have to go from sometimes back to the steps, but she shows like some of these steps, like let's say you find a data set with characteristics that you want. Let's say this data set has 10,000 examples. Then you go and remove like low quality instructions, and you end up with this amount of samples. Then you you also remove the ones with low quality responses. So first, you remove low quality instructions. Second, low quality responses. Let's say you end up with this amount. Then for 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 the 3,000 examples that have low quality responses, you go and pay for a service, or you yourself go and create high quality responses for those. So you're now back at 9,000 high quality examples. Then you realize that you don't have enough coverage for any specific topic. So you manually go and create 100 examples using for this topic. And then, well, 100 instruction templates. And then you use another model to just synthesize 2,000 instructions using these templates. And then you go and pay for a service, or you annotate those instructions, and you end up with a data set with 11,000 examples. So that's kind of an ideal scenario of annotation, the annotation scenario, where you start with the data set, figure out what's wrong, what's good, try to improve it, try to label yourself, try to improve the instructions and responses, and try to create more for specific topics that you found that you don't have enough coverage. We already started speaking here about synthesized instruction. So speaking about that, data augmentation and synthesis, it's been a long-term goal in the industry to just generate data cheaply. That computers generates data, and we don't need to go and find for other sources. We don't need to just go and pay someone to annotate or to craft very nice instructions. There are two approaches of doing that. One is data augmentation, and the other is data synthesis. Often people just say data synthesis, and they also uh, refer to augmentation, but formally, those two things are different. So data augmentation, very popular in computer vision models. And actually, example here is, that imagine that you have a real image of a cat, And if you flip that image, let's say 45 degrees, then you have a new image of the same cat, but it's a different image for your model, and basically teaches your model to also look at cats in different angles. That's data augmentation. If you have a image in black and white, no, you have an image in colors, and then you put it in black and white, then that's data augmentation. You have two examples. You're training your model to also be able to handle uh, black and white images. That's producing more data. You can add noise to the image, so you can like simulate uh, photos taken by 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 less quality cameras. Uh, so you train your model to also handle high quality photos and low quality photos. That's data augmentation. That's something that computers can do, and it's very cheap to do. So at the end, you are basically creating examples from real data. Whereas data synthesis, you generate data to mimic the properties of real data. So, for example, you can simulate how a mouse, a cursor, moves through a web page to generate data for what bot movements would look like. So at the end, augmented data is derived from real data, whereas synthetic data isn't real. And if we're gonna speak more about methods to create like synthetic data. So why do we want to do this? Why do we want to synthesize data? Basically, with the goal to increase data quality, uh, data quantity, and data coverage, as a goal to mitigate privacy concerns. Uh, because if the computers are creating, synthesizing new data from trusted sources, sources that are compliant, then we are mitigating a lot of privacy concerns there. You also want to synthesize data to distill models. It's a concept that also we're gonna speak in a couple of slides. But it's basically sometimes you want to train a model to imitate the behavior of another model. Usually you want to train a smaller model to work kind of similar to a bigger and more expensive model. And the idea of doing this is to have a cheaper and faster model. So you distill the model using data generated by the original model. So basically that could mean that you train the smaller model with the outputs of the bigger model. So you actually are distilling its knowledge, let's say. So traditional methods to do this, traditional techniques, um, there are rule-based data synthesis and simulation, basically. Here's an example of rule-based. So for example, let's say we want to augment data to mitigate biases. So let's say we have this sentence, she's a fantastic nurse, and we want to mitigate gender biases. So we augment that data and we have a sentence that is, he is a fantastic nurse, oh, and also she is a fantastic doctor. So from a single template, from a single record, we now have two more examples. Same example with the CEO of the firm, Mr. Alex Wang. And then we have another one that is the CEO of the firm, Mrs. Alexa Wang. And just like that, you have a template and you augment the data on the template. That's a rule-based data synthesis, and you end up with more examples, and you also mitigate some biases. So you now have also coverage for other topics. Then about AI powered data synthesis. Let's say what is here, because I don't remember. It can be used to synthesize the instruction response or both. Okay, so you can generate what is called example seed tasks or templates. So let's say you have this instruction, brainstorm a list of possible New Year's resolutions, and you have this output. So that this is your seed, this is kind of a template. Then this template, you can pass it to a model, usually a high quality model to generate more examples that follow this same template. So the model goes and generates an instruction or an output like, okay, brainstorm creative ideas for designing a conference room. And then it has an output. Then you this is your seed, and let's say you have 10 of these, and from each of those, you ask the model to generate 10. So you end up with 100, yes, with 100 generated tasks. That's a way to synthesize data by using a model. Of course, this has some limitations and some concerns. One is quality. So these generated tasks examples can also be low quality, and basically we shouldn't use this technique on things that we can't verify. So if yeah, basically if we can verify easily the quality of this generated task, then yeah, we can do it. But if we can't, then we're gonna lose quality control there. There's also another limitation of superficial imitation. Research shows that the imitation models are good at mimicking the style of the teacher model. The teacher model is this bigger model, right? But might struggle with factual accuracy and generalization tasks outside the training data. So we might end up with very high confident models that are wrong because they were thought to imitate a bigger, more complex model than themselves. So they're gonna have their patterns, the output of their responses, the, the 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 patterns in their responses might be like super confident, but their reasoning might be off. There are also some concerns about potential model collapse. So some researchers have shown that like using AI generated data to train model themselves causes some irreversible defects in the resulting models. So and having their performance to degrade with time. So basically, we just use models to create data, to train other models, and then we continue doing that. At some point, we might reach a collapse, and the quality and the performance just we can go back from it. And there's also a big concern about data lineage. So let's say we have a big model that we use, an X model that we use to generate trained data. And if this bigger model was trained on data that had like copyright violations, then your model, the smaller model, the one that the steel model, might also violate copyrights, even if you're training, even if the data that you gather, it's complied with copyrights rules. But if you generated some other data from a model, there might be like copyright violations in there. So yeah, it's gonna be a obscure data lineage because you cannot go back from it easily to track where that specific example came from. So yeah, that's about data synthesis. Then about model distillation. So yeah, as we were saying, the idea here is to have a smaller model, usually often called a study, that is trained to mimic a larger model. And why do we want to do this? Basically, to produce smaller models for deployment that have a comparable performance of the bigger model. For example, the student model can be trained from scratch, like Distilbert, a popular model, or fine-tuned from a pre-trained model like Alpaca. So for example, Alpaca behaves very similarly to TextDaVinci, and it is only 4% the size of TextDaVinci. So performance almost the same, but Alpaca is just 4% the size of this model. Let me see. Here's a question here. Michael says, in my work, we have used a hybrid system, an AI judge that can also generate synthetic data. That's nice. If the AI judge deems an output to be bad, we ask it to suggest a better output. The suggested outputs are still reviewed by a human, but it can make the reviewer just easier. That's cool. Yeah, that's really nice. Use case there, and also yeah, great to have also like a human in the loop to just confirm that also that everything looks good. So yeah, you still have like this reviewing process, but indeed if the model does the hard part, reviewing is just relative, is just simpler, right? Reviewing is often easier than producing, and the models can produce a lot, and then humans are good at reviewing. So yeah, that's model distillation. And the last section, let me just check that is indeed the last section. So yeah, we talked about data creation already, data augmentation and synthesis, and then data processing, which is actually relatively simple. So data processing, we can the first step is to actually like the first pre-processing step is to actually like inspect your data, be familiar with it, know it. Don't just, okay, I have a data set, let's train the model. Because probably you're gonna get like poor results. So ideally you want to understand where your data come from, how was it processed if you're getting from external sources, who else use it, and with which purpose. You want also to get familiar with the token distribution, with the inputs length, with the response length. This is gonna also kind of let you know if you have enough coverage for the use case that you want to do, or for the task. If you want your model to be able to craft like long responses, and you plot the response length of your training data, and it's just like 10 tokens, so just simple sentences, then it's gonna tell you, hey, you need to go and find other more data with longer responses, right? So you need to get familiar with the token distribution. Also with the topics and languages in your data. If you want your model to be confident about the, I don't know, sports, but your data doesn't have sports or not sports topics, then it's telling you that you don't have the coverage for that. How unique are the examples? Are there any examples with the same query but different responses? And also, are there any examples with the same response but different queries? That is also going to teach you about the, what's it called? I just forgot. I forgot the word. The consistency of your data. So if you have examples with the same question but different responses, then if they're not valid, like it shows like lack of consistency there, and the same goes to same responses with different words. Uh, those can be valid or those can be an issue depending on the context, right? Another stuff that we carry in the processing step is deduplication. So as we already spoke, duplicate data can skew the data distribution and introduce biases into your model. So duplication can also cause test set contamination, as we said. And sometimes like duplications don't hurt the model performance, but they at the end can waste time and compute, right? So and by wasting compute, you're wasting money. So sometimes it's good to deduplicate deduplicate records. Deduplication can also, or duplication, the meaning of the duplication can also depend on your specific use case. Chip speaks about that, yeah, the engineers and the scientists at the end needs to come up with the definition of, okay, what's a duplication, consider a duplication for our use case. So is it at document level? So we have the documents that are exactly the same, or is it paragraph level? Okay, there's a document and there's a paragraph that is like that are specifically the same, or it's sentence, or it's document level. So depending on the level of granularity, it's like the level of granularity is going to depend on your use case. Common ways to find or to deduplicate your data. She spoke about these three ways: pairwise comparison. So you compute the similarity score of each example to the other and see. So you are able to easily find duplicate sentences or records or documents. Of course, this can be very expensive, right? Because you have to do one versus the other for every example. So it can be, yeah, very expensive to do. You can use hashing techniques, so hash examples into different buckets and check only among examples that fall in the same bucket. Or you can use dimensionality reduction techniques. So you use one of these techniques to reduce the dimensions of your original data and then do the pairwise comparison. So at the end, it's a bit cheaper than do it just with the raw examples. Then also important in the processing steps, clean and filter your data. So yeah, so clean data also it's kind of the same definition of high quality data, or it's very similar. So yeah, you want clean data to make your model performance and also be safe. There's one of these articles by Databricks that found that removing like a strange markdown and HTML tokens improved their model accuracy by 20%, while reducing their input tokens length by 60%. So just by removing weird stuff that they didn't care about, their model performance increased and their token length got reduced. So probably they got a better model for a cheaper price. So that's great. But yeah, also clean data. Yeah, also can also be tied together with policies. So often you want to to eliminate to delete anything that isn't compliant, sensitive data, copyright data, or data that is considered toxic. So basically, in the clean and filter stage, it means okay, let's remove low quality data. And that definition of low quality is going to depend on your use case. So yeah. Then format data. So yeah, once you deduplicated your data, you have it clean, you have it in the right, you can put it in the right format that your model is expecting. So that can mean like if your model expect pairs of inputs and responses, means that putting in those pairs and also then using the appropriate tokenizer and to have it in the right format. Yeah. By the end of the chapter, Chips also mentions like some data processing tips um, and says that, okay, yeah, this can take just a few hours, depending on how big your data set, or it can take days. Uh, so some of the tips are like, um, yeah, like these steps, you don't need to make them in order. Like sometimes cleaning is easier to do after you already duplicated, or sometimes it's easier to do a first clean and then duplicate stuff. Of course, formatting often comes at the end, right? So you don't want to like format everything, waste a lot of time formatting, and then having to clean stuff. Uh, yeah, she suggests to always do like trial runs to validate that the processing scripts work as expected. You don't want to like find that you have an issue in your preprocessing pipeline after you spend hours in training, right? So you want to validate that everything there works. And also a very useful tip here: don't change data in place. Like let's say you have a data set, the raw data always work on a copy. Like, okay, I have the raw data here, save it somewhere, create a copy, and uh, let's start there. She suggests two reasons. Uh, why? Because probably this raw data can be also useful for other use cases, and other use cases might have different rules for preprocessing. So you don't want to just preprocess everything and just have it for one use case. And also because you could corrupt data by doing that, right? If you're changing data in place, at the end you lose the raw one. And if you add a bug or something that is not good to your original data, then it's very hard to just go back, right? And that's it, I think. That's the end of the chapter. Quite, yeah, practical chapter. Speaks about everything data related, very useful in AI, ML, and everything related to the data space. I don't know if you have any questions. Feel free to put them. I see a comment from Michael here. It says, just out of my practical experience, it always helps to automate your data processing pipelines as much as possible. Many times the pipelines can end up messy setup scripts, notebooks. Yeah, it's true. Often in the beginning, like also like I found myself, okay, I'm gonna do this pre-processing. Let's say you're working on a notebook and you have processing steps. Okay, I process data, then go back and work about training, blah, blah, blah. Then months go by or days go by, and I have more data and I need to go and reprocess it in the same way I did it for the initial step. And sometimes you forget. If you are messy and you don't have things automated, then probably the 2 months version of yourself wrote a messy script where you had to remember to run step two first and then run the other step, and then you're gonna end up with data being preprocessed differently. So yeah, it's a good idea that all these preprocessing pipelines are as automated, tested, validated as you can. So you ensure that everything that goes to the model is as you expected. Yeah. That's about.
Well, yeah, I didn't have a question as much as a comment or more of my experience. Like I remember I was working on this project which was to create like a shopping assistant. I would type in some query and some e-commerce products would come up. It's just like a mock project that I was working on. And what I found it interesting was just to find out the data set of what are the most common queries on e-commerce sites was a bit difficult. That I couldn't find that that kind of data set, and maybe I did something wrong or something. But I just found that interesting that you used to have a data set of what are the most common user queries on e-commerce websites, and then just to improve the quality of the query and the response, one of the steps involved actually creating a data set where for a given query I have to write in bad responses as well as good responses. That's how it would improve. And it just seemed a lot of work. How do you create those kind of data sets automatically where for a given instruction or let's say query, automatically you need to fill in bad responses and good responses, good matches, bad matches.
Mhm.
So I was wondering if anyone had any more practical experience, how they encountered issues like these in terms of finding relevant data sets or creating there. And the chapter was definitely helpful on a lot of the approach or the overview of it, but just more for more practical situations like these. Someone who has spent a lot more time in the data trenches, if they could share some experience, that would be helpful. But just more like a comment sharing. And thanks, Santiago, for taking up the chapter.
Welcome. Yeah, I don't know if anyone has experience there with like crafting data sets. One experience that I have is that at work. So I work at a company that develops methods to monitor machine learning models, right? Uh, Most of our techniques are to monitor traditional machine learning models, not AI, Gen AI models. Uh, but we came up with this Gen AI methods that we wanted to test how the performance of these models evolve. So in order to test that, we need to have like a nice evaluation framework, a set of data sets to evaluate the performance of those models. And uh, so we had to basically create like golden data sets ourselves.
Yeah.
And that required like a lot of time, like just to properly label and create responses for just, I think it was just 200 posts, like 200 samples. Took me
Wow.
like a week of work of just like double checking stuff. Because
Yeah.
let's say I don't remember I think it was like it was from a wiki Q&A dataset.
Yeah.
It's fun. It's famous. So it has like, I don't know, what's the capital of France? Right, a basic example. And the expected response is, okay, the capital of France is Paris. So you have, okay, input, output. But then I send it to the model that we trained, and it says, I don't know, something. Perhaps
Yeah.
says just Paris, or perhaps it says the capital of France, the European country that is located next to, I don't know, next to Germany, next to Italy, I don't know, is Paris. So it's a correct response, right? But it's different. So
Yeah.
it's very difficult to just measure if they are the same or not. So I had to go there and actually look at the responses in order to calculate a score. Sometimes I had to go on fact check the stuff. So yeah, it requires a lot of manual process to just create a few hundred examples.
Yeah. And I find it interesting. We work on these fancy techniques, and suddenly at some point we need to actually manually create some data sets. they just sit down and create those data sets. I think it was,
Yeah.
we had to do triplet loss or something. This we had to create that kind of good bad matching on there. But yeah, very
Okay.
interesting.
But I think it's a underrated technique because I think if you as a model developer actually go through that process of manually creating data, you learn a lot about the actual problem you're trying to solve and what are
Yeah.
the like nuances and edge
Mm,
cases and stuff like that.
yeah, yeah.
Indeed.
Actually, for me, there was a very powerful sentence in the book, in the chapter, when I was skimming through. It's like, train the model, or input the data to the model on the kind of behaviors that we expect. I mean, so basically, we need to connect data, the input data, and the output behaviors. I was like, okay, I mean, it seems obvious once mentioned,
Yeah.
but it's a very powerful. If we just keep that in mind at the center of it all, that my input data should determine the output behaviors, I think it's quite powerful
Yeah.
there. Yeah, yeah, but just on
Indeed.
the one point that you mentioned, Santiago, and there's this recursive data set usage, something that was there, and I came across that line even in the book as well. What does it mean exactly? Is there a specific example that you have? There was something that you mentioned as recursive. I mean, not to use recursive data.
Mm.
It was, I'm just trying to see my chapter. Do you remember that?
Yeah, I think I remember. I think it was on the one of the risks of using
Yeah,
uh, synthetic data, like
yeah.
let me share again.
Yeah,
So when
recursively
it's
using AI-generated data in training causes irreversible defects in the resulting models.
uh,
Um,
indeed.
yeah, yeah.
So
What
yeah,
is
one
this?
example is for example that I don't know. You see how often ChatGPT, Claude, all of these LLMs have a kind of way to speak. They are often very verbose. They often like
Mhm.
use a specific language that you can hint as a human reader. You can tell if something was created by an AI or by a human, right? It's we
Yeah,
kind of still kind of notice. So one example is that if we just continue creating AI generated data and
got
using
it.
it as an
Mm.
input to train further generations of LLMs,
Yeah, there's loss of
then
fidelity. Yeah, yeah, it makes sense. Yeah,
then that the specific kind of tone is
yeah.
gonna
Progressive
get even
degradation.
bigger. Yes.
Yeah,
So yeah,
yeah.
it's gonna be harder for us to just go back and make the model, I don't know, right more naturally, more human like. That's just an example, but yeah, that's this model collapse is what it's referring.
But that is really interesting because I think we are already in that world where, if you think
Yeah,
about all these models are creating a lot of content that is making its way onto the internet. It's hard to detect what's AI generated, what isn't, and we are training new frontier models. So
mm,
I think it's something that we can't escape. It's going to happen, and we have to just deal with it.
Yeah.
For the
Uh,
pre-training folks, have you guys looked at Dolma? It is from Allen AI, AI2. I've just posted the link in the chat, and it is a pre-training data set as well as a toolkit. So the toolkit, uh, using the toolkit, you can use like it's a high performance solution. I think so. If you look at it, it uses Ray 2 for high parallelization, across nodes, and like you can use the C4 dataset, the C4 snapshot that is available, and like you can do data deduplication, data curation, and other good things with the built-in tigers. Like you can have your own tokenizer that is being attached, and fast deduplication. You can have support for custom tigers, like if you want to jump in and find out the high quality tokens with your uh, particular language if you are talking about the multilingual aspect of it. So, like, since I am currently working in a research direction in this end, so like I thought I will be sharing
Nice.
this.
Nice. Yeah, I wasn't aware of this, but yeah, it's a cool, like, practical tool to basically, yeah, implement all the nice tips that we discussed today. Nice.
Yeah.
Very cool.
Plus, you can raise issues and you can ask the authors. There's a Discord too, I think so. And like if you want to delve deeper, since we are also in the process of writing our own pipeline for this whole stuff, and yeah, if you guys want to be involved in this kind of a process, then like yeah, feel free to.
Very good. Any other comments that you have? No. Then for next week, we're gonna discuss about inference optimization chapter 9, and I wanted to ask if there's any volunteer to lead that chapter. Next week is May 4th. May the 4th. So yeah, anyone want to take the lead there? Yes. No. Nobody. I'm gonna give 10 seconds more of just awkward silence. Nope. Then okay, I'm gonna ask in the chat, and if not, I'll try to do it myself during the week. Okay. Then that's it. I don't know if you have any other additional comments, concerns. Nope. All right. Then nice. Was a really nice discussion. See you next week and on Discord. Goodbye. Have a good day.
Thanks, Enrico.
Welcome.
Take care. Bye.
Bye.